Hello. Hello, can you guys hear me? Can someone tell me if my audio is alright? Okay, we'll start now. Uh, Similar to last week, there'll be 10 questions which are from the previous year, so they will be similar to your current quiz questions, assignment questions. First question. Consider the minterm expression y of ABCD equals sigma m of 0, 1, 2, 3, 8, 9, 12, and 13. Which among the following options represent the dual of the simplified version of y? Okay. To solve this, first we have to find a simplified version of y. They're given y in terms of minterms. Y is sigma m of 0, 1, 2, 3, 8, 9, 12, 13. Let's write a k-map for this to simplify the expression. So here I will have the variables AB and here I'll have CD. 0, 0. So if we fill the k map, and this is m0, so m1, m3, and m2, and this is m8, this is m9, this is m12, this is m13. So in terms of variables, this will be a bar, b bar, a bar, b, ab, ab bar. This will represent c bar, d bar, c bar, d, cd, and cd bar. Okay, so we have to form the largest group possible, which is a power of 2, so that all the ones are covered, and we can form one group like this. We can form the other group like this. So these two groups will cover all the ones, and they are the largest groups of powers of 2 that we can adjacent cells of powers of 2 that we can have. Okay, now in the first group, the group at the top, we can see that a bar, b bar are constant, and c bar is changing to c here in this transition, so that variable will be gone, and d changes to d bar here, so that variable will also be gone. So this top group, this represents a bar, b bar, and in the second group, which is a quad, you can see that a is remaining constant and b is changing to b bar, so b bar will vanish from the expression, and here c bar is this is remaining constant, and d bar is changing to d, so d will vanish. So this group represents AC bar. So the simplified expression for y is a bar b bar plus AC bar. Okay, if you have any questions, you can stop me in the middle. Now the question says, which among the following options represents the dual of the simplified version of y? So the dual of this expression, what you have to do is, you have to replace AND operation with OR operation and replace OR operation with AND operation. And you have to replace ones with zeros, zeros with ones. Here there are no ones and zeros in the expression, so you just need to replace the operator. So here you can see that there is an AND operation here, A bar and B bar. So that has to be changed to an OR operation, A bar plus B bar. This plus will be changed to a dot AND operation. This dot, which is an AND operation, is changed to OR operation, A plus C bar. So this is the dual of the simplified version of y. Then to select which among the options, we have to see. You have to check with the options. There are different ways in which this expression can be implemented depending on whether you have NOR gates or NAND gates or AND or OR gates. But one thing we are certain is the output expression, the dual of the output expression, contains only A, B, and C. It does not contain D. So from the options you can see that there's a D bar in option B and there's a D bar in option C. So both these options can't be what we are looking for. So it has to be either option A or option D. Now we need to do a slight manipulation here. You know that AB bar, or let me use different variables, XY bar is equal to X bar plus Y bar, right? So X bar Y bar whole bar will be equal to X bar complement plus Y bar complement. So it will be nothing but X plus Y. So X plus Y can be written as the whole X bar and Y bar, the whole complement. So if we do that with our given expression, Y will be equal to wait, X plus Y complement is X complement and Y complement. So X complement plus Y complement, the whole complement will be XY. So here we take this as X and take this as Y. So now what we have is Y is A bar plus B bar complement plus A plus C bar complement, the entire thing complemented. So this thing is a NOR operation. This is also a NOR operation. The entire thing is also NOR operation. So these three are all NOR operations. So if you look at option D, you get this is A bar plus B bar whole complement. This is A plus C bar whole complement. So Y will be equal to A bar plus B bar whole complement plus A plus C bar whole complement, the entire thing complemented, which is the expression that we have. So the right answer is option B. So we'll have to do slight manipulation and check with option A and option D. If there are no options given and it's just a subjective type question, then you can use NAND gates also. And whatever is the circuit you get is fine. Any doubts? Okay. We'll go to question number 2. We have a logic circuit with 4 input and 1 output, and the inputs are only BCD inputs, that is, they go only from 0 to 9. 10 to 15 are ignored. They are taken as don't care conditions. And this circuit generates a logic high when the input has even number of logic lows. That is, when there are even number of zeros in the input, the output will be a 1. The correct SOP expression for output F is. So first let us write the truth table for this function. Yes, Tanmay, what do you want to ask? Do you have a question? Tanmay, you have raised your hand. If you have a question, you can unmute yourself and ask me, or you can type it in chat. Okay, I'll continue with the question. You can ask me whenever you want. Okay, we have to first write the truth table for this. A, B, C, D are the inputs and F is your output. You could directly write it in a K-map if you have experience, but since you guys are starting out right now, you can first write the truth table and then write it down in a K-map. So with 4 input variables, there can be 16, 2 power 4 input combinations. So 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, triple 0, then 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1. I'll fix this later before uploading the notes. That's 13, 1, 1, 1, 0, 14, and 1, 1, 1, 1. So we have 16 combinations like this. But since the input is only a BCD input, from 10 to 15 we don't care. So the output for these are don't care, X's. And from 0 to 9, the output is high only when there are even number of zeros. So in 0, 0, 0, 0, there are 4 zeros, which is even, so the output is 1. In 0, 0, 0, 1, there are 3 zeros, which is odd, so output is 0. Again, in the next combination, there are 3 zeros, which is odd, output is 0. 0, 0, 1, 1, we have 2 zeros, which is even, so output is 1. Next one is 0. 0, 1, 0, 1, there are 2 zeros, so the output is 1. 0, 1, 0 also has 2 zeros, so the output is 1. Next combination has 3 zeros, which is odd, so the output is 0. 1, 0, 0, 1 has 2 zeros, which is even, so the output is 1. So that's the truth table. And looking at the truth table, we can write the K-map for this. And remember, in the question they have asked the correct SOP expression for the output. So we need to consider the min terms, the product terms. The output will be a sum of products. So if we take AB here and CD here, A bar, B bar, A bar, B, AB, AB bar, C bar, D bar, C bar, D, CD, CD bar. For 0, 0, 0, 0, the output is 1. So this is 1. And then the output is 1 for 0, 0, 1, 1. So here you can see this is 0, 0, 1, 1. So this is 1. Similarly, this will be a 1, 0, 1, 0, 1. And 0, 1, 1, 0 also has a 1. And 1, 0, 0, 1 also has a 1. And we had don't cares which will come in these cells. So you can check from the truth table. Okay, now we have to simplify this. So we have to group as many, we have to form as large a group as possible so that all ones are covered. So to cover this one, I can form a quad. A square like this which has 4 of these cells is called a quad. To cover this one, we have to form a pair. This is just a single cell, you can't cover it any other way. This one can be covered by wrapping around like this. So this one and this X are adjacent, so that forms a pair, and then these two form a pair. So there are how many blocks? 1, 2, 3, 4, 5. Now the output expression in each group only contains those terms that are not changing within the group. So here if you take this quad here, B is changing to B bar, so B is eliminated, and C bar is changing to C, so C is eliminated. So this block gives you AD. This block, nothing is eliminated, it's just a single cell, so it's A bar, B bar, C bar, D bar. This cell here, A bar is changing to A, so A is eliminated, so B, C, D bar. This cell or this pair, A bar is changing to A, so A is eliminated, it's B bar, C, D. And this one, A bar is changing to A, so that will give you B, C bar, D. So your output is simplified output. The sum of products form is Y equals AD plus A bar, B bar, C bar, D bar plus B, C bar, D plus B, C, D bar plus B bar, C, D. Which is option D. I forgot to write the option for first question. Alright, we'll move on to the next question. Question number 3. Find the dual of the following expression using Shannon's expansion theorem. The theorem is given here: f of x1 x2 up to xn is equal to xn complement and f of x1 x2 up to xn minus 1 comma 0 plus xn and f of x1 x2 x4 up to xn minus 1 comma 1. So to take the dual of this expression, we have this to 0. So to take the dual, you have to replace AND operation with OR operation. So xn complement or f of x1 x2 etc., and you have to replace zeros with ones. So this 0 will become 1. So this is the, could say this is the first term, this is the second term, and they are being ORed here. So that OR will change to AND in the dual. So you will get AND, again this AND will change to OR. So you'll get OR f of x1 x2 etc. up to this 1 will change to 0. So this is the correct answer. And among the options, which one is it? It's option A. Okay. Alright. We'll move on to the next question. Which of the following statements is or are correct? So you guys try this one. This is simply this was taught in the class, so it's just knowledge based. So tell me which option it is in the chat. I'll give you 2 minutes. After 2 minutes, if you don't know, I'll tell you the answer. Okay, I hope you gave it a go. So which of the following statements is or are true? Let's see. Taking or of min terms, canonical sum of product form of Boolean equation can be obtained. That is true, right? The canonical sum of product form is nothing but the summation of min terms for which the output function gives you a high value. So let's see. So if we had to write the SOP form for this function, here this would be min term number 0 m0. This is a bar, b bar, c bar, d bar. That's the min term corresponding, and the min term is just an expression that is high only for one particular input combination. So what we mean by the min term corresponding to 0000 is that it is that term containing all the input variables which becomes high only when this input combination is given, and which is low for all other input combinations. So a bar, b bar, c bar, d bar, only when you give 0000 will this become high. If any one of the inputs is a 1, the complement of that will be one of these variables, so the complement will be 0, and when it is ANDed with the other variables, regardless of their value, you will get a low output. So that's what a min term is. So if you find the min terms corresponding to all the input combinations where the output is 1, you can just sum them up to get the expression for the function. So this will be m0, this will be m3, and in the truth table the value given by this input combination, if you write it in order, so this is in binary, in number systems you will see later, this is a 0, this is 3, and this is 5. So the index of these minterms is labeled in the same way, m0, m3, m5. So you take all the minterms that give you 1 and simply add them up. So this f will become, in the canonical sum of products form, m0 corresponding to this plus m3 corresponding to this plus m5 corresponding to this is m6 plus m9 I think I missed out a combination here. Plus 6, that's a 7, 0, 1, 1, 1, which gives you 0 output, and then there's 8. So it didn't matter because this was giving you a 0 output anyway. Okay, so this is the sum of products, canonical sum of products form of this function. So you get it by ORing the minterms. So it is true. The first statement is true. This is true. Similarly, when you do the product of, if you want the product, canonical product of, okay, this is called canonical product of sum because no simplification has been done here. You just take the minterms and add them up. So this thing is not a canonical sum of product of sums. That's just the SOP or POS one. So canonical product of some form of the Boolean equation can be obtained by taking AND of max terms. We saw that in the lecture. You just, wherever there's a 0, you take the max terms corresponding to, wherever there's a 0 in the output, for the corresponding input combination there will be a max term. You take that max term and AND it with the other terms. So 2 is also true, and you can go back and check in the lecture that in SOP realization, if in a two-level SOP realization, we can have an AND or a NAND NAND. While in two-level POS realization, you can have OR and or non-OR. All these things were taught in class, so I won't be teaching them again. You can go back and check in the lecture notes. So 1, 2, and 3 are correct. 3 and 4 are just a variation. They are switched OR and or not with SOP and POS. So among 3 and 4, only one can be correct, and it is 3. So 1 to 3 are correct. Therefore, the option C is the right answer. Okay. Two-level realization of SOP and POS. Let me see. This one, right? See here, sum of products form. The expression is just the sum of a few product terms, right? It's literally in the name. So this, if you write it out, let's see, if you write it out in terms of A, B, and C, M3 is nothing but A bar B C. M5 is A B bar C. M6 is A B C bar. M7 is A B C. So that's the expression in terms of the variables if you write it in terms of A, B, and C. So you can see that all these expressions are 3 input and expressions, right? So A bar B C, you can get it from feeding A bar B and C into a 3 input AND gate. So that's what they have done here. So they have fed this A bar B and C. We're assuming A bar is already present. It's A is already present in the complemented form. So each of these expressions, the inputs are passed through an AND gate. So you get A bar B C. This is this term. A B bar C, it's this term. A B C bar, it's this term. A B C, and you can see in the expression that these four terms are simply all together. So you pass it through a 4 input OR gate. So all these expressions, this is an OR gate. There are 4 inputs. They are A bar B C, A B bar C, A B C bar, and A B C. So you will get this at the output. So there are two levels here, right? One level is contains only AND gates, which you use to get each of these smaller expressions, which are the min terms, and then you use an OR gate to add only those min terms that you want. So this is another level. This is one level. This is the second level. So there are two levels in this circuit. That's why it's called a two-level implementation. Similarly, in the POS form, if you write out this expression m of 036, 0 will be a plus b plus c, and 3 will be a plus b bar plus c bar, and 6 will be a bar plus b bar plus c. So each of these terms here that are being added is a max term. You can get it by passing those corresponding inputs through an OR gate. So A, B, C through an OR gate will give you A or B or C. And then all the expressions are taken together and passed through an AND gate. So here the AND gate, you will get the entire expression. So again you can see that there are two levels. The first level has only OR gates. The second level has AND gates. That's why this first one is called AND OR, because there are AND gates first and then there are OR gates. AND OR two level implementation. POS, it's called OR AND. So that's AND OR and OR AND. That's the two level implementation. And then the next thing you have to note is that this is an AND OR expression, right? First, variables are ANDed together. A, B are ANDed, C, D are ANDed, E, F, there's an AND. And then all those three are ORed together. So it's an AND OR implementation. But if you, let's say you complement it twice, as given here, then there's a Boolean algebraic law that says that x complement whole complement is nothing but x, regardless of what expression it is. So it's the same thing logically. And then you use De Morgan's law to apply De Morgan's law to the inner expression. So De Morgan's law, what does it say? A plus B plus C whole bar will give you A bar and B bar and C bar. So each of these terms is complemented and ANDed together, and there was a complement outside that. So now these two expressions, this one and this one, they are logically the same. That is, for the same combination of inputs, they'll give the same outputs. Only thing is, the way you implement it is different. You can use different gates to implement those. So here you can see AB whole complement, that's a NAND operation. CD whole complement, that's a NAND operation. Similarly, EF whole complement, that's a NAND operation. And if you take each of these AB complement, CD complement, EF complement as a variable, then this entire thing is just nothing but XYZ complement. Right? That's also an AND operation. So instead of using two different types of gates, AND and OR, you're using the same type of gate, NAND and NAND. So that's how you get NAND and NAND from AND OR. Why we do this is sometimes, a lot of the times, the circuit that we have, it will have only one type of gate, NAND gate. Depends on what you have with you. If you have only AND OR, you can use AND OR. If you have only NAND gates, you can convert it to NAND. Or if you have only NOR gates, you can write it in POS form. Also, your gates will have other specifications, right? Fan in and all. So they may be different in an AND form compared to AND OR form. So you might be able to manage with one type of circuit and not with the other. So these are mostly things that depend on what you have in real life. So that's the two-level NAND implementation. Similar for NOR also. Okay, did you understand? Alright, we'll move to question number 5. Determine which of the following can be associated with the output waveform of the circuit at y. Initially x was 0, then it is made 1 and kept at that value. Consider a finite propagation delay of the logic gate. So here you can see the input, one of the inputs to the logic gate is just y. The output is, this is called a feedback, because the output is taken and fed back into the input. So what will be your output? The output of an AND gate is simply you AND the inputs and not it. So y is actually xy complement. Y is xy complement. Initially when x is equal to 0, there's no problem with this. Y is just 0 and y complement, which is nothing but 0 complement, which is 1. So here there's a 1 that is fed back in the input. So the output is nothing but x and 1 whole bar, which is nothing but x bar. And since x is 0, it's 0 bar 1, everything works out. So it's consistent. There's no problem with the circuit. Now the problem arises when x is equal to 1. When x is equal to 1, y is equal to 1 and y whole bar. It's nothing but y bar. So y equal to y bar, that doesn't make any logical sense. 0 is not equal to 0 bar. 0 bar is 1. So 0 can be equal to 1. This is one of the basic postulates of Huntington postulates for Boolean algebra, right? There are two distinct elements, 0 and 1. They are not the same. But hopefully, since we are dealing with a circuit in real life, then there will be a propagation delay in the gate. By propagation delay, what we mean is that if the input here, let's say it was initially 1, right? If it changes to 0, the changes in the output don't happen immediately. It will happen after some time. So what will happen in this case is that initially this y was 1, y equal to 1. Then you changed x is equal to 1. So that will make your output y is equal to y bar. So this 1 changes to a 0. This will happen after some delay, and then the input to this circuit will become 0 now. So once that becomes 0, the output should go to 1 again. At 0 and x is 0, complement is 1. But that will take some time, it won't happen immediately. So the change in this input from 1 to 0 will be reflected out at the output side only after some time. So it's still fine. So it will slowly change to 0 after some time. Then again this will again change to 1, and it will keep oscillating like that. So the correct answer is option D. The output keeps oscillating. Y is equal to y bar. So whatever you have as the output at one point of time, after some time it will just get complemented and come as the output. So this is called an oscillator because it's oscillating between two different values, 0 and 1. So the answer is option D. Okay, and this only happens in practical circuits. If it was an ideal circuit, then this couldn't really happen. Y can't be just equal to y bar. At that point, something inside the circuit might just burn. Okay, I will move to question number 6. which of the given min-term expression is implemented in the following circuit. So first let's write down what expression it is. For the first NOR gate, the inputs are A and B, so you'll get A plus B complement. This is A plus B complement. Second NOT gate, the inputs are NOR gate, the inputs are B and C, so this is B plus C complement. For the third NOR gate, the inputs are A and C, so this is A plus C complement. And all these three are fed to another NOR gate, so the output is OR of all these three inputs, the whole thing complemented. So this is actually what we have. So you can simplify and write this using De Morgan's law. It will become A plus B into B plus C into A plus C. Okay, but this thing has it's kind of similar to a product of sums form. So you have to convert it into a sum of products form. So there are two ways we can go about this. I'll write out both ways. First way is you try to convert it into a canonical product of sums form initially. So here you can see that this term has only A and B. It doesn't have the variable C. So you have to introduce that variable C somehow. What you can do is, since C bar is equal to 0, C and C bar, that's just a basic law. A and A bar is equal to 0, B and B bar is equal to 0. All these things will be 0, so you can just add them. A plus B plus C and C bar. It won't change anything. Like this thing is 0. So this in effect is the same expression. Similarly, whatever term is missing, whatever variable is missing, you can add the corresponding term. A bar and A plus B bar plus C. The next property we'll use is x plus yz is equal to x plus y into x plus z. So this doesn't happen in normal arithmetic, but in Boolean arithmetic, the plus operation, the OR operation, distributes over the AND operation. So what this will become is A plus B plus C into A plus B plus C bar. Similarly for the other two things, B plus C plus A, B plus C plus A bar, and A plus B plus C, A plus B bar plus C. The next thing that we use is A and A is nothing but A. So A plus B plus C comes 3 times, but even if you AND it 3 times, in the end you will be left with only A plus B plus C. So you can write just one A plus B plus C, A plus B plus C bar, A bar plus B plus C, that's this term, and then this term A plus B bar plus C. So this in the max terms or the canonical product of sums form, you can write it as pi of what are these terms? This is 0, this one is 1, The third one is 4. Next one is 2. Okay. So when you're writing maxims, if there's an uncomplemented variable, that corresponds to 0. And if there's a complemented variable, that's 1. So this is actually 0, 0, 0. 0, 0, 0 in binary will be number 0. So that term is here. It will be 0, 0, 1. So that will be the number 1 in binary. So it will be 1, 0, 0. That's 4. You learn this when you learn number systems. This is 0, 1, 0. That's 2. So that's how I wrote down the max terms. Okay, now they have asked for min terms for this, right? So to write the min terms, all you have to do is take the complement of these numbers. So with 3 variables, there can only be 8, 2 power 3, 8 min or max terms. They will go from 0, 1, 2, 3, 4, 5, 6, and 7. So whatever is not there in the max terms form, if you include that, I will give you the expression in terms of min term. So 0, 1, 4, 2, you exclude those. What you're left with is 3, 5, 6, 7. Right, so the answer is option A. So this is one way of doing it. The second way of doing it is you have y is equal to a plus b and b plus c and a plus c. You multiply this out using distributive law and actually write it down. So ab plus ac plus b plus bc and a plus c. Again, that's ab plus ac plus ab plus abc plus abc plus ac plus bc plus bc. You use distributive law and write it out. And then if there are similar terms, you can just write down one of them. Because again, similar to a dot a is equal to a or a is also equal to a. So it's ab plus bc plus ac plus abc. Those are the terms you'll be left with, and you can take ac common these two terms. Right, ab plus bc plus ac into 1 plus b. 1 plus anything is just 1, so this term is just 1. So you'll be left with ab plus bc plus ac. Now again, this is in sum of products form, but it's not in canonical sum of products form. In canonical sum of product form, each of these terms should have all the variables included in it. This should have abc, so this should have abc, and this should have abc. So when you have product terms, the way you introduce the uh, variables that are not present is by ANDing it with, first time you AND it with c plus c bar. Because a plus a bar is nothing but 1. And 1 and anything is nothing but that variable itself. So c plus c bar is 1, ab and 1 is just ab. So the expression did not change logically. So this will be a plus a bar into bc plus ac into b plus b bar. This will give you abc plus abc bar, and this will give you abc, but we already have abc, so I'll just not write it down. The other term will be a bar bc. Again, this will give you abc, that I will not write it down since it's already there in the expression. So a b bar c. So from this you can write the min terms. And when you're writing min terms, If it's in uncomplemented form, it's a 1. If it's in complemented form, it's a 0, 0, 1, 1, 1, 0, 1. This is binary 7, this is 6, this is 3, and this is 5. So the terms are 3, 5, 6, 7. So you get the same answer in both ways, it's just a different way of simplifying. Answer is option A. Okay, now operator alpha is defined as B alpha A is equal to B complement plus A. Which of the following is true? The operator alpha is associative, alpha is commutative, alpha is neither associative nor commutative, alpha is both associative and commutative. I'll give you 2 minutes to try this yourself. Try it out, it's not very difficult. If you don't know how to do it, at least you can think of intuitively what do you think? What will happen? Is it associative or is it commutative, or is it not any of those things? I'll give you 2 minutes. Think about it. Okay, well, let's try to solve it. So, first thing we have to know is if there is an operator, binary operator star, that operates on a binary operator operates on two numbers or two elements of some set A star B, let's say, then this star operation is said to be commutative if A star B is equal to B star A, and it's said to be associative if A star B star C is equal to A star B star C. This is in general for any operation. So what the commutative property means is that even if you change the order of the operation, the result will not change. For example, 2 plus 5 is 7 and 5 plus 2 is also 7. So by changing which number comes first, the answer will not change. That's the commutative property. So here A alpha B is A prime plus B, and B alpha A is B prime plus A. These two things are not equal. A prime plus B is not the same as B prime plus A, so it's not commutative. Alpha is not commutative. How do you check whether these two expressions are same or not? Easiest way to do is, most straightforward way to do that is by writing down the truth table. If you write A, B, and you write A prime plus B, A plus B prime, 0, 0, 0, 1, 1, 0, 1, 1, 4 input combinations are possible. And you see what's the output, plus B or if it's A plus B prime. I'll just do for one input combination. So if A is 0 and B is 1, the first one is 0 prime plus 1, right? Which is 1 or 1, which is nothing but 1. So A prime plus B will give you 1. But the second one is 0 plus 1 prime, which is nothing but 0 or 0, which is nothing but 0. So for the same input combination, the output is different. First one gives you 1, second one gives you 0. So those two expressions can be the same. Okay, it's not commutative. Let's check if it's associative. Generally, there are more, you could say a lot of operations are associative. In general, most operations will be associative that you can come up with in real life operations, but they might not be commutative. So there are, let's say there are more functions which are associative than those that are commutative. That's just a general way, but for this function, let's do A star B star C. This is A alpha B alpha C. What this means is, first you do A alpha B, so you get A prime plus B. Then that you consider this as one variable, say x, and you do x alpha C. That will give you x prime plus C, which is what? Which is nothing A prime plus B whole prime, or C, which is nothing but A B prime or C. Now let's check A alpha B alpha C. This is A prime plus B alpha C. This is A prime plus B prime plus C. Similarly, you can write down the truth table or give some inputs and see whether these two are the same, and you'll find out that these two expressions are not the same. So A alpha B alpha C is not equal to A alpha B alpha C. So what this means is that the order in which you do the operations actually matters. When you are just multiplying numbers, 2 times 3 times 4, if you do 2 times 3 first, you'll get 6 times 4 is 24. Or if you do 2 times 3 times 4, if you do the 3 times 4 first, you'll get 2 times 12, which is also 24. So the order in which you do the operations doesn't matter in normal multiplication. But there are operations where this order matters, and one such example is this. So this example is just to show you that there are operators which might not be commutative and associative. Some operators can be only associative but not commutative. Some can be only commutative but not associative. There are all kinds of operations, and You can't go just based on your intuition. You have to actually work it out and see whether these operations are have these properties or not. Alpha is not associative. So it's neither associative nor commutative. I think someone actually gave the answer. Yeah, Aditya, Ravindra, and Vinod Kumar both have said it's neither. Yes, it's neither. It's neither of those properties hold. So it's option C. Okay. Consider the circuit given below. The value of W and X and Y and Z. So first we have to write down what W, X, Y, Z are. W is A is one input, the other input is B, and it's fed to an OR gate. So it's A or B. X is, all of them are OR operations, two input OR operations. The inputs are different also. For X, the inputs are A and B bar. So the value of X is A or B bar. For Y, the inputs are A complement and B, A bar plus B. Z is both the inputs complemented, A bar plus B bar. So the value of W and X and Y and Z. So they're adding everything. W and X and Y and Z. A plus B and A plus B bar. A bar plus B. A bar plus B bar. This you can write as A plus B bar, right? Right, using the distributive law. This can be written as A bar plus B bar. And B bar is nothing but 0. So this is A. Here also B bar. So this is A bar. A and A bar is 0. This is just from the basic laws. So the answer is option A. Okay. Yeah, it's option 1. Which of the following is the correct product of max term representation of this expression? So let's write it out. F is, first we use De Morgan's law on this term. What do we get? A B bar complement and A bar B complement. That's what we get. This can be thought of as x plus y whole bar, which is equal to x bar and y bar. Okay. Now again, this thing we use De Morgan's law again. So it's of the form xy complement, which is nothing but x complement plus y complement. So this is nothing but A bar plus B and A plus B bar and CD bar plus C bar D. You multiply this out using distributive law. What you'll get is A bar A is 0, B bar will also be 0. What you'll be left with is A bar B bar and AB. So it's AB plus A bar B bar and CD bar plus C bar D. Now we again use the distributive law. This can be written as AB C D bar plus AB C bar D plus A bar B bar C D bar plus A bar B bar C bar D. In terms of min terms, what will this be? This will be 1 1 1 0 1 1 0 1 0 0 1 0 0 0 1. So in terms of min terms, it will be 14 13 2 and 1. So in terms of product terms or max terms, it's the rest of the terms. So for 4 variables, the terms go from 0 to 15. It's 2 power 4 minus 1. So it will be 0, 3, 4, 5, 6, 7, 10, 11, 12, 15, which is option C. Okay. Then the last question. Consider a Boolean function f of a, b, c, d such that f of 0, 0, 1d is equal to 0, f of 0, 0, cd is equal to 0, f of 1, 0, 0d is equal to 1, f of 1b, 1d equals b plus d, f of a, 1, cd is equal to ad plus c. The number of literals in the minimal sum of products expression of f is. So first we have to get the sum of products expression and then we have to minimize it. There are 4 variables a, b, c, d. So 4 variables, there will be 16 input combinations possible. We'll write them out. It's 5, 6, 7. I'll write them side by side. 8, 9, 10, 11, 12, 13, 14, 15. Okay, first thing we know that f of 0, 0, 1d is 0. So if a, b and c are 0, 0 and 1, then regardless of what the value of d is, the output is 0. So here a, b, c are 0, 0, 1. Here also a, b, c are 0, 0, 1. Regardless of the value of d, both these inputs will give an output 0. So this is a 0 and this is a 0. Second thing is f of 0, 0, cd is 0. That means if a is equal to 0 and b is equal to 0, then regardless of the value of c and d, the output is 0. So the combinations where a and b are 0 are the first 4. So a and b are 0 here. In that case, regardless of the value of c and d, the output is 0. So these two are also 0. That's what we find from the second equation. The third one is f of 1, 0, 0d is 1. So if a, b and c are 1, 0, 0, regardless of the value of d, the output is 1. So that's here, here, both these are 1. You see a, b, c are 1, 0, 0. Next thing, f of 1b, 1d is b plus c. So if a equals 1, and C equals 1, the output is B plus D. So which are those? Here A is 0 in all these things. In all these combinations A is equal to 1. So in this combination A and C are 1, A and C are 1 here, here and here. So in these combinations the output is B plus D. So B is 0, D is 0. So this is 0, B plus D. B is 0, D is 1, 0 or 1 is 1. B is 0, B is 1, D is 0, 1 or 0 is 1. And B is 1, D is 1, 1 or 1 is 1. Okay. Next thing is f of A1CD is AD plus C. So if B is equal to 1, the output is AD plus C. So B is 1 in this combination, this input combination, this, and this. So those are the remaining uh, input combinations for which we haven't filled out the table. So in all these combinations, the output is AD plus C, AD plus C, where A is 0, C is 0, D is 0, so this entire thing is 0. Here A is 0, C is 0, D is 1, so again it will be 0. In both these things C is 1, so if C is 1, regardless of what value A and D take, the output will be 1. So both these are 1, right? Next we come to these two, AD plus C. A is 1, D is 0, C is 0, such AD is 1 0 or C is 0. So it's 0 0, this thing is 0. And finally A is 1, D is 1, C is 0. AD plus C is 1 or 0, which is 1. So this is the truth table. Now we have to write the K-map to simplify this to get the minimal sum of products expression. So let's go ahead and write down the 4 variable K-map. I'll write AB here and CD here. And then we fill out the ones. So this is M6 and this is M7. M6 is here. This is M7. So those two are 1. M8 and M9 are 1. M8 is here. M9 is here. 11, M11 is 1. So this is a 1. And then 13, 14, 15 are all 1s. So this is 13, this is 15 and this is 14. So this is the K-map. Now you have to form large groups of adjacent cells. and which are powers of 2. So here we can't form a group of 8 cells, so but we can form a group of 4 cells. So the first one is this, that's one group, that's a quad. Second one is this, and the remaining one can be covered by a pair. And now when we write out the expression f is equal to, for the first, for this block, a bar is changing to a, so a is eliminated, and d is changing to d bar, so d is also eliminated. So the expression for that block is bc. Expression for this block is b is changing, c is changing, cd. Expression for this pair is ab bar, and d is changing from d bar to d, so it's ab bar c bar. So the output expression is ad plus bc plus ab bar c bar. And the question they have asked is how many literals are there in this expression. So literal is just a variable in complemented or uncomplemented form. So here you can see there's 1, 2, 3, 4, 5, 6, and 7 literals. So the answer is 7. Which one is that? It's option D. Answer is option D. Alright. Okay. So there's one more thing I wanted to tell you guys. What is it? Uh, there's this society called Institute of Smart Structures and Systems. So like you might have heard of societies called IEEE, ACM and all, where journals, conferences all take place. They publish journals, they conduct conferences, such stuff. So IESSS is one of them, and mostly IIC professors are here. And they have one feature called PMRF Student Lecture Series. So various PhD students give lectures, and I am one of those students. So you can see here that I am taking a course on problem solving, digital electronics problem solving. So similar to the problem solving sessions I'm doing now, I will be conducting additional problem solving sessions there. So I'll post the link to this website here. So there's a registration form. You can give your name, email ID, and other details, and you can register for that course. Wait a minute. So this is not part of nptel, this is part of IESSS. It's a different platform, but I'll be doing problems that are not that I have not already done on that platform. So these problems that I am doing right now, they are from previous year assignments. So each assignment will only have 10 questions and you will only get 10 problems in every session. But here I'll solve problems from textbooks, from gate papers. So there'll be a lot more variety of problems. And if you are interested, you can join. It has nothing to do with nptel. So I'll post the link in the chat box. So I'll try to make those lectures also available through recording through that platform IEEES. So if you feel that you need more practice with problems and you want to see more type of problems that might occur in competitive exams like GATE or some textbook problems, then you can register for this course and attend. It will start from February 29th. There will be two sessions each week for 6 weeks. So by that time you will have theoretical knowledge from this course. So problem solving will be much easier for you guys. So this is just completely up to you. If you feel that these problem solving sessions are helpful, then you can join this one also. Okay, that's it for today. If anyone has any doubts, you can ask now. Or if there's some concept that you didn't understand from the lectures, you can ask and I'll try to explain as much as possible. Also, you can register for this course. I don't think there's any cost for this. It's just free of cost, I think. And even if you can't attend the live lectures there, you can still have recorded problem solving sessions. So I'll try to get post recordings there also. So if you're interested, register for this. Alright, guys, I'll just stay here for the next few minutes, and if anyone has any doubts, you can ask me. Otherwise, you guys can leave. Thank you for attending. Hello.